Hello, my name is Raneem and I'm going to talk about the optics of the eye and the different optical corrections. The basic function of the eye is to form an image of whatever object being looked at on the retina. This image formation is done by the combination of the cornea and the lens, which behaves like a convex lens. And the focus length of this lens is adjustable by the muscle attached to it according to the distance of the object, so that its image is always formed on the retina in normal situation. The simple relationship between the focal length f of the lens and the distances of the object and its image is as following. And I'm going to talk about it later, so I'm just going to skip it a little bit now. And in the human eye, as the image always needs to be formed on the retina, the eye is fixed to be the distance between the lens and the retina, which is about 0.017 meters. And the focal length of the lens need to be adjusted as a function of the distance of the object. And we have this formula and these numbers for that. In the vision, we have something called far point and near point. The near point is the closest point in which the person can see clearly, and the far point is for furthest part. As we can see in the plot here, major adjustment of the lens is needed only when viewing objects within the range of about ½ a meter. For example, the focal length needs to be at 0.0145 meters of an object at 0.5 meters, or 4 meters, sorry, or 0.0163 meters for an object at 0.4 meters. And to view any object further away than 0.5 meters, the lens needs to be pretty relaxed, so that S is very close to 0.017 meters. Let's now talk about the optical corrections. What does it mean? Optical corrections are slight modifications of geometrically correct lines for the purpose of making them appear correct to the eye. And let's start with the first one. Or let's first tell what nearsighted means and what the farsighted means. We have two different abnormalities mainly. I'm gonna, of course, we have more, but I've chosen to talk about myopia and about hyperopia. Myopia, or as we can also call it, nearsighted, and we have hyperopia, which is also called farsighted. Nearsighted is that a person who is nearsighted can see things clearly if they're nearby, but in case they are further, then it gets blurry. And for a farsighted, it's vice versa, basically, it's the opposite. So starting with myopia, most common causes are that the eyeball develops longer than normal, as we can see here, or it could be due to refractive powers are stronger than normal. And the nearsightedness is experienced by almost half of population. It's just good to know. Now let's say that you're trying to look on a very far object, infinity, it's not infinity, but we can say it infinity, means that the ciliary muscles now in the eye will pull on the eye, trying to stretch the lens. And when the lens is stretched, it will pull the focal point further to the left. The reason why the eye needs to do that is because the object's very far away, causing nearly parallel light rays to reach the eyeball will form an image very close to the focal point, basically behind it, so behind the retina. And this will make the rays scatter and make, as you can see, and make this fuzzy vision. So what we need to do here is basically naturally the muscles would just let go, but that is not enough. We need to do something more. So for that, we need to use those lens of correction in front of the eyeball, and they will cause the rays to go divergingly, and they are diverging lenses, and they will cause the image basically, first of all, the focal point to go back, and then an object that is far away can form an image right on the retina. Now you can see much better. So basically optic correction use is divergent or minus or concave lens, also as we can call it. Next is hyperopia. Hyperopia is either due to the eyeball is too small or the refractive power is too low. And as a farsighted person, it's a bit different. So now no problems with further objects, but with closer. So in that case, when the muscles will pull on the eye and the eye gets thinner, the focal point moves further back and the parallel lights and the image will be formed behind the retina so that they can't see far clearly. But then what happens when the object is placed closer? The muscles will let go, lens shape will change, and focal point will get in. So it gets in here. But lens doesn't bulge because there are no muscles doing that. This means that the focal point does not get to the right enough, which means that the image will then fall far past the retina, and we get fuzzy vision. Since the muscles are relaxed, they are not allowing the lens to go to the right, or it does basically not let it to bulge. So we will use the converging lenses now, making the focal to move further to the right, which will then bring the image to the right and then on the retina, and you can see clearer. So this is how we correct the vision, whether you're nearsighted or if you are foresighted. Now I just chose to use an example just to apply the formula that we mentioned in the beginning, basically the lens equation. Example, if we have a myopia person who has a far point. A far point, as we said before, it's the furthest point that the person can clearly see. In my example, I chose it 50 centimeters, but of course it can be different. And beyond this, it's being unfocused and blurry vision. Objective is to put some corrective vision lenses on with a diverging effect, as you can see here. This is not how it looks like. It's so the lens basically. And now we will cause the object that is very far away to get closer and get into the far point over here. How do we do that? Well, by using the lens equation. So we have the S here is the object distance, S prime is the image distance, and F is the local length. So we're trying to find the focal length of that lens, and let us then plug in the numbers that we have. For S infinity, or we can also say 100 feet, 50 feet, whatever you want, but normally we use the infinity. So we apply it in this form. Of course, we notice that the image is in front of the lens, which means that the image distance is a negative distance. So this is why I plugged the 50 here by minus. And now we calculate it all. We know that 1 by infinity is 0. So we will get this result. And if we turn the equation, we will get the final result as minus 50 centimeters. And so that must be the focal length of the lens. But if you get into a lens store, you will not ask the person in the store to give you the type of the lens. You will tell the power of the lens. So what we do is that we convert or we calculate the power of the lens, and we use this F that we got here, minus 50 centimeters, but this time in meters. So we need to convert from centimeter to meter, and we will get the minus 0.5 meters. So this is the focal length of the lens that the person needs if he has myopia, and with these numbers. This was just an example, remember. Then when you get the units, you need to, you need to go further on. You get this is the result, and you just calculate it. So you need power of minus 2 diopters. Diopters is the unit for power. So you just tell the person that unit lens is labeled minus 2 diopters, and now you can see the object much clearer. Yeah, and that was all for me. Thank you so much for listening, and hope it will be for an advantage. Thank you.